would like to thank Rafa and Jerome and the Science Organizing Committee for inviting me to provide the opening talk at this conference. It's certainly an honor to do so. I'm getting signals that I'm not as loud as I should be. Is that better? We're here, of course, to talk about the results from two missions, and I suspect those two missions don't need very much of an introduction to this audience. The first is the CoRoT mission through the French National Space Agency with a boost from ESA, PI Annie Baglin, and the Kepler mission, Bill Barucki as the PI through NASA. I personally would like to start with thanking a few individuals that I've been very fortunate to work with over a large number of years at this point. Tim Brown is my close colleague, going back now 35 years probably. And I've worked with Bill Barucki, Dave Koch in the past, John Jenkins on the Kepler mission now for fully 20 years. And at the fully 20 years level as well are Hans and Jan. And more recently, the last 5 years in particular, as things got very exciting with Kepler data, Bill Chaplin. In approaching this meeting and the opening talk, I thought I would key off the word revolution to start with and simply try to ask the question, is it really justified to have that word in the title of this conference? Have the sciences of exoplanets and asteroseismology been revolutionized because of the existence of space photometry? So I started by looking at a couple of dictionary definitions. The first, of course, is a forcible overthrow of a government. That obviously doesn't apply to us, but we are talking about French and American missions, and we did share revolutions over 2 centuries ago, back to back. Fortunately, the French helped out in ours, and maybe we helped inspire theirs. Those revolutions have certainly changed our countries fundamentally and the world as a whole. Oftentimes for the better, maybe once in a while for the worse. A second definition that comes up is a dramatic and wide-ranging change in the way that things work or the way that people look at them. And that fits what we're talking about pretty well. To put things in further context, I look to a well-known 20th century revolutionary, Vladimir Lenin, and he said a revolution is impossible without a revolutionary situation. Well, I'm going to spend most of my time trying to describe what the revolutionary situation was that led to the supposed space revolution for exoplanets and asteroseismology. Lenin also said, it's impossible to predict the time and progress of revolution. It is governed by its own more or less mysterious laws. And I think that we could note that there couldn't be anything more mysterious than how NASA, ESA, and other equivalent agencies work. And in an alternate universe, we could very well be having the same conference, the Space Photometry Revolution, but it might be called Mons Symposium 3, CoRoT3-KASC-7 joint meeting. And should point out that neither of these two missions, Mons or Eddington, unfortunately made it to space, but that doesn't mean that the time and effort spent on these missions and other missions like them were without great value. It's only because of the large community effort with Mons and ESC and Prisma, STARS, Eddington, the ESA series, the small Canadian telescope MOST, and other small space telescopes that we built up enough momentum that we could have eventually a couple of missions, CoRoT and Kepler, succeed. And if we were in this alternate universe, the talk might be presented by Ian Roxburgh. But as you know, Eddington figuratively went up in smoke, and you're stuck with me. So I want to start in 1994 as setting the stage for how our science has developed in terms of space photometry. First of all, it's a nice round number of 20 years ago exactly, but there were lots of things happening in 1994. In terms of results, there wasn't much yet for either exoplanets or asteroseismology. There were exotic exoplanets. The binary pulsar planets were known. There were near misses in asteroseismology, but nothing that any of us would call real successes. And I should own up to the fact that I'm using asteroseismology in the narrow sense of solar-type stars and red giants. So for instance, I'm not covering classical pulsators in my talk, or ROP stars, or white dwarfs. Of course, there were fantastic results already in 1994 from white dwarfs, ROAP stars, Don Kurtz, ROAP, Don Winget, Steve Kowaler, and others on white dwarfs and classical pulsators. And those were fundamentally important and kept the flame alive, if you will, for asteroseismology to the point where we could do the real thing, the solar-type stars and red giants. In '94, there was an annual reviews article, Asteroseismology, by Tim Brown and myself. There was a Global Oscillations Network group meeting entitled Helio and Asteroseismology from Earth and Space. And there were presentations at that meeting from CoRoT by Claude Catala, STARS, Malcolm Friedland, who's here, and for the Kepler mission. And I also presented a paper at that mission about photometric methods for asteroseismology, making arguments about whether or not you could do photometric detections of solar-type oscillations from the ground. That was based on a large-scale 4-meter telescope network that several of you in the audience were involved with. And we concluded that it wasn't outright physically impossible to do it from the ground, but it was pretty much impractical, and that we really ought to do it from space on a 1-meter class telescope, and gave the example of FreeSip. There also were conference proceedings from a small meeting that Bill Barucki had put together of what astrophysical science might be done with his exoplanet hunting telescope. And I looked at that recently. Tim Brown and I think had independent papers that did a very good job of outlining why astroseismology should be on Kepler. In 1994, CoRoT was proposed as a concept mission to CNES, with Claude Catala as the PI, and FreeSip, Frequency of Earth-Sized Inert Planets, was proposed at the NASA Discovery mission level for the first time by Bill Barucki. Now, it's interesting that Kepler changed its name about halfway through from FreeSip to Kepler, but the science stayed exactly the same. CoRoT managed to change its science in a fundamental way. Initially, it was convection and rotation of stars, but then they decided to redefine the acronym to be convection, rotation of stars, and transits of planets. So they kept their name but changed the science. Now, I don't want to imply that nothing of interest happened before 1994. There was a lot of activity in astroseismology. So for instance, 10 years earlier, there was a News and Views article in Nature, Beginnings of Astroseismology, by Douglas Goff, one of the founders of the field of astroseismology, that discussed 2 separate papers, one French, one American, claiming detections on different stars. And as was very common in this time period, and unfortunately remained common for a long time, the results of these papers were refuted once better data came in from other groups. So progress over 1995 to 1999. Of course, the big result in 1995 was the exoplanet discovery of 51 Peg B. And that was followed very quickly by confirmation by another group. And these and other groups made other such discoveries throughout this 5-year time interval, discovering about 5 such exoplanets. However, during this time, for those of us who were around then, there was still a fair amount of controversy. There were people that argued that these were not really exoplanets. After all, they were just M sin I detections, and if sin I were unfavorable, then these weren't planetary masses after all. Well, that skepticism was very firmly rejected when transits were first detected on HD 209458, done by 2 independent groups at the same time, one led by Tim Brown, Dave Charbonneau, the other by Greg Henry. In terms of astroseismology, there were no usable astroseismic successes. And again, I'm restricting this to solar-type stars and red giants. And I don't mean to insult anybody by that. There were lots of groups, I was involved with one of them, working very hard on trying to make astroseismology succeed in that time period. There were groups in the United States, there were groups in France, Tim Betting and folks in Australia, the Danish group was active, and surely others that I'm not mentioning. We were really trying hard to detect oscillations on other stars from the ground. But as you know, it's very hard. The signal is really small. And the efforts to advocate for a space mission continued to intensify through that period. One thing in planning this talk, I, of course, went back to older literature to review what the progress was, and I came across the series from Betting and Keltsen, or Keltsen and Betting. They seem to be interchangeable, starting annual or frequent chronicles of ground-based progress. And those were great papers to read at the time, I did, and they were also very valuable, as I said, to review in planning the talk. But the interesting thing that I noted here is that there were as many reviews as there were successes in the field over the roughly decade that these chronicles were appearing. Now, there was one qualified space photometry revolution that occurred in this 5-year period. Two groups discovered that the expansion of the universe was accelerating. These groups were fiercely competitive, published papers in 1998 and 1999. And these two papers were based in part on HST time series space-based photometry. And I think that this certainly qualifies as a revolution that was fueled by space photometry. But of course, we're not talking about that here today. Over the years 2000 to 2004, one of the big steps was a space photometry result. This by now iconic light curve of HD 209458 through transit as observed by the Hubble Space Telescope and published by Tim Brown. And today showing such a light curve at a meeting would be very uninteresting because Kepler has created thousands of light curves that are of a better quality than that. CoRoT has produced I don't know how many tens, hundreds that look that good. Most, and even occasionally from the ground, we can get time series of transits that are very impressive. But 14 years ago, that was an extremely impressive light curve. And I would like to think, and it may even be possible, that having that actual proof from a space-based telescope that you could get fantastic photometry on transits, which were very new at that time, may have been a success that helped out the final existence of CoRoT and Kepler very much. This came before Kepler had been selected for final approval. Over this period, and this remains true all the time throughout the 20-year interval, the pace of radial velocity-based exoplanet detections accelerates. That's always been a very rapidly developing field. In asteroseismology, this is the time period where there finally, from the ground, was real success that nobody would doubt. The Boucher and Carrier paper on Alpha Centauri, you could just look at the power spectrum and it felt like that was a real detection of individual frequencies. And it was of high enough quality for the first time to support interpretations. And very dramatically compared to the large number of studies that had come before, when other people went to better telescopes to get observations, they found similar results and provided improvements rather than refuting those results. There also were positive findings in this period on giant, subgiant, dwarf stars. Not a large number, I haven't tried to list them all, but still it remains about one per year that's coming out in a positive way from asteroseismology. During this time period, there were multiple missions that were selected, but there were also multiple missions that were dropped. Fortunately, of course, we know of two missions that were kept, both of which were finally selected early in this period, and those are Kepler and CoRoT. I want to spend a few minutes on three side issues to set the stage for the general development, primarily of asteroseismology. The first is how the Kepler Asteroseismic Consortium came to be, and I suspect most of you sort of know this story. With Kepler, asteroseismology was always a part of the science program. Even in 1994, in the first submission to the NASA Discovery level, Asteroseismology was described as a key part of the science, small part, but key. And Tim Brown and I were the astroseismologists within the Kepler science team. We proposed to NASA a total for the full mission cost to support astroseismology of $750,000, and that was primarily for postdoc support for us throughout the mission. Tim and I always knew that that was not enough support really to do justice to the observations that we expected from Kepler astroseismology. We were only planning to do solar-type stars and red giants. We weren't going to do RR Lyraes and ROAPs and all the other things that are interesting as well. That would be the GEO program. So we started talking to Jan about whether or not he might be interested in helping us out with his expertise in theory and interpretation. He certainly was interested, but Jan was also, at that time, one of the bad guys in the sense that he was very deeply involved with the Eddington mission, and the Eddington mission was very much our competitor at that point. We were both trying to get the finishing line first. Well, something changed very shortly for Jan. In October of 2003, ESA canceled Eddington. And at that time, very quickly, talks with Jan about Kepler collaboration picked up quite a little bit. And a few months later, something else happened. NASA dropped all monetary support for astroseismology within the science team. So even though we hadn't asked for very much money, they said you can't have any money. Fortunately at that time, Kepler was not canceled. It could have been. Just as Eddington was on the chopping block, there were discussions at NASA headquarters about killing Kepler. There also were discussions about dropping the short cadence observations entirely, no astroseismology. And Tim and I both argued that at least keep the short cadence observations. And I think the only reason we did was that the flight software already existed and the cost to NASA of keeping it was essentially zero. So fortunately, the capability was there to go forward. So at that point, Tim and I had a mission, but we didn't have any support, and Jan and Hans had Danish internal support for Eddington, but they now no longer had a mission. So it was very natural that we got together, and Bill Barucki was very supportive of us, of that effort, and that led to the creation of CoRoT and KASC, and of course it's through the vision of both Jan and Hans, and primarily Hans in terms of managing and thinking through how to set it up, that the real origin and success of KASC has occurred. The second topic that I want to cover, and you probably don't know about this one, is how Kepler got its sharp point spread functions. There are people today that will tell you Kepler flew with intentionally soft PSFs, because every good photometrist knows that a soft PSF would be better for giving you good photometry. And if you look at our proposal to NASA, pre-2003, and the emphasis in this first quote was in the original proposal, pointing noise is suppressed by spreading the PSF over many pixels. And we had a requirement that the flux on the pixels have at most 20% of the light within the central pixel, and we wanted this to be uniform over the field of view. So we wanted soft PSFs. But in mid-2003, Ball Aerospace, who generally did a fantastic job developing Kepler, admitted that they had dropped the ball, pun intended, in terms of implementing a soft PSF. They came back to Bill and the science team and said, we sort of lost track of the fact that you guys wanted a soft PSF. It simply was easier to implement optics that are normal, that give a sharp PSF. So we're going to have up to 68% of the light in the central pixel. The vast majority will be greater than 30%, and there's going to be a very strong field dependence. Well, this is about as far from what we wanted going into the mission as could be imagined. And we recognized in discussions with Ball that a few more $1 million and a few months launch delay would be able to fix that problem and get us back to having soft PSFs. But this was just at the time when NASA was having a financial emergency, Eddington was being canceled. It wasn't the time to ask for more money. So there was an emergency declared within the science team to go off and investigate this, and John Jenkins and I in particular addressed what the effects would be on our data of having very sharp PSFs. And John came back and said that due to the exquisitely good guiding we expect with Kepler, among other things, that it should be fine. And I came back and looked at the effectiveness of the astrometry to eliminate false positives from background eclipsing binaries, which was becoming more important within the science team at that point. And for that application, the sharp PSFs were actually an advantage. And we had also recognized by that time, based upon HST experience, that we thought we could use saturated stars. And of course, more stars would saturate with sharp PSFs. So we said, let's go for sharp PSFs. And during commissioning, we did everything we could to focus the telescope the best we could to get sharp PSFs. And what we realized is shown in blue here, that the sharpest PSF is at 63% light central pixel. It's seriously undersampled. In no way is that a soft PSF. The good news is that if you plot quality of photometry versus sharpness of the PSF, it's the sharpest PSFs that provide the best photometry. So we lucked out on that. We didn't get what we wanted, but we got what we needed. The final aside is that the European and American sides were very competitive during this time period. That, of course, is no surprise. On the table were Eddington, Kepler, same scale mission, and Kepler somewhat smaller. And we were sometimes a bit, well, not just a bit, but downright dismissive of each other. And I certainly did my part in that. I can remember saying in the 90s and early 2000s that Kepler would outperform STARS Eddington for asteroseismology. And I did that even recognizing that Eddington was primarily having a goal of asteroseismology, while Kepler was very secondary for asteroseismology. And I didn't think it was even worth mentioning CoRoT in that context. I thought Kepler would be dramatically better. And I still believe that would have been true, that Kepler would have been better for asteroseismology than Eddington. Surely I would get objections to that. But what is interesting is this paper that came across my desk in July of 2009. I was requested by the editor of Astronomy and Astrophysics to give a second referee opinion on a paper by Mosser and Apercho, and I did that saying I think this is a fine paper and ought to be published, but gee, they're a little bit negative in their description of the capabilities of Kepler, and maybe they should be more positive. I won't read the quote, but just paraphrasing it, they said that CoRoT would provide better photometric performance than Kepler. Over 90-day intervals, Kepler probably would be able to get the large separation detection on F-dwarfs and subgiants. And golly, if the science team took all 4 years' worth of data that they hoped to collect, then on a few of the very best G-dwarfs, they could probably get a solid detection. And the asteroseismology program of Kepler, after all, was primarily about getting large separations on a few exoplanet host stars. So as a result of my suggesting that they might want to be more positive, and this was already 4 months after launch of Kepler, and after I had seen the data, but of course nobody else had seen data, I think they changed one word here. They changed lower to different. But in context, I think it's clear that their expectations were not too high at that point for Kepler. Fortunately, I think their expectations have surely changed because some of the best results for the Kepler mission have come out from these authors. So it's very good that even though we were dismissive of each other, we quickly got beyond that. Up to mid-2009, the revolution was nearly at hand, but we weren't there yet. With exoplanets, space was becoming very important, with HST, MOST, and CoRoT providing results. Asteroseismology, a very impressive radial velocity result from the ground, was on Mu-Era. And this had become a very vibrant science, but without space, there was still only about one detection per year, and that one success per year came at very great effort of state-of-the-art spectrograph on usually a large telescope, sometimes a network of telescopes. There were CoRoT results on dwarfs during this period by Eric Michel and other papers shortly thereafter, and those were really wonderful. But in terms of quality, they were better, but not dramatically better than what you could do from the ground, and they weren't remotely close from the quality of solar observations, and there weren't very many of them. I think it's fair to say that the promise of space photometry for both of these sciences was very great, and the anticipation was becoming very palpable at that time. It just strongly filled the air. 2009 is when I would put the start of the space photometry revolution, and I would put it at a very specific time, namely when CoRoT published the first results on red giants. The papers that were published in May and accepted in June, respectively, from Joris de Ritter and Saskia Hecker, showed that red giants were going to be very good for doing astroseismology. Up to that time, prominent theorists like Jan, observers, I think we all had doubts about whether or not red giants would show oscillations that would be of any real utility for doing real science. The Hecker and de Ritter papers from CoRoT completely changed that. It was obvious that red giant oscillations had long lifetimes, and we would get wonderful results out. So that was the opening salvo of the revolution. The second part of the revolution was a quiet one, in the sense that it came from Kepler, and it came at exactly the same time. In May and June is when the first data came down from Kepler, 9 days and 33 days worth of data. I think it's fair to say that I was the only person in the world that cared about asteroseismology that had access to those data. And of course, I plotted up time series of all the short cadence observations, generated power spectra of all the short cadence observations, and I can remember during that time period just sitting there in awe day after day with what I was seeing. It was really fantastic. And I had been with Hubble Space Telescope for 20 years, so I was used to seeing pretty amazing things. But Kepler was far better. It just blew me away. I could easily see G-dwarf oscillations in a month worth of data. And a plot of effective noise was just as exciting for me. Over a very broad magnitude range, we clearly were getting noise at the optimistic level that we hoped to with Kepler. And furthermore, it appeared that nature herself was going to be very kind to us. So for instance, the CoRoT results on giants were on luminous giants. But I could see from the first month of Kepler data that all the way down the red giant branch were just beautiful oscillations. And of course, those were published several months later when the data got out a little bit. So the revolution was clearly at hand. It started from CoRoT. Kepler was contributing data of better quality at the same time, but it wasn't out there yet, but would be shortly. It's interesting to look at the revolution in numbers, and the first line here is exoplanets in 5-year blocks. The second is asteroseismology in 5-year blocks. CoRoT first enters in 2009, Kepler first enters in 2014, and the CoRoT fractions are small everywhere except for the critical block of asteroseismology 2005 to 2009 where it dominates. That's where the revolution for asteroseismology started. Kepler dominates the asteroseismology block in the last 5 years. For exoplanets, things aren't so clear because over the set of 5-year intervals, it looks like a geometric progression that's always increasing. And for most of the time, all of that is radial velocity work or transit detections from the ground. In the final block is the only time that space with CoRoT and Kepler contribute very much, and about 50% of the numbers there are from space. When you consider, however, so I might argue that there was no revolution for exoplanets in space photometry. But when you consider the qualitative advances, which I'm not taking the time to talk about, but will be talked about at this whole conference, it's really clear that there really was an honest revolution in both of these sciences that is attributable to space photometry from CoRoT and Kepler. And we can ask how space photometry has changed our sciences. In '94, the quest was for any discovery that someone else would believe, however modest, would have been great. And now, of course, as we all know, there are a stunningly large number of rock-solid results in both exoplanets and asteroseismology. and a wonderfully wide range of qualitative advances, whether it be knowing the transition point in mass for exoplanets being rocky to gaseous, or be it the asteroseismology discovery that we can leverage off the G modes and red giants to say something about their deep cores and their rotation, or whether it be combining results from exoplanet observations and asteroseismology of their host stars to really get down to understanding interesting details about those systems. It's interesting to look at a paper from 1996, 20 years ago roughly. I chose Jeff Marcy for the example. It was Marcy and Butler. If we look at a Jeff Marcy paper from now, we have a particle physics flavor. It's Jeff Marcy plus 100 of his closest colleagues. Now, it simply is a fact that because we're relying on space missions and how those work, that the nature that we do science has changed. And I'm sure that there are many positive aspects to that. I suspect there are a few negative aspects to that. So this is my last slide, just a few closing thoughts. In 1994, Tim and I had an Asteroseismology annual reviews report, and nicely bookending that, in 2013, Bill and Andrea had a very similar review on asteroseismology of solar type and red giant stars. Now, 20 years ago, we could only talk about the foundations and our hopes for the future. Fortunately, Bill and Andrea had it much easier in the sense that they didn't have to talk about hopes. They had all kinds of positive, amazing results to talk about thanks to CoRoT and Kepler. And just in the way that these two reviews bookended what I would call the prelude to the revolution that started in 2009, and what I would expect is the end of the revolution last year, although obviously we're too close to it to know what the end of that revolution is. Revolutions have an end. I think it was last year. Just as the way that those presentations bookended things, Andrea will be giving the closing talk at the meeting. It's really been an exciting time for me. I was involved with both the Hubble telescope and Kepler, arguably the two best missions that have existed for science. And it's clear that success will breed continuation in this field. And it's very good that TESS, Plato, and other missions are being accepted and will go forward and provide very compelling advances and surely many qualitative as well as quantitative advances in the future. Thank you.
So, if there are any questions?
Well, thank you, Ron, for this very complete review of what have happened over the last 20 years, which brings back a lot of the frustrations that happened, but also the elations and the jubilations that have taken place. Just want to add a small correction to one of your first view graphs. When CoRoT was proposed to CNES, it was already Annie Baglin who was the PI for it, but simultaneously Claude Catala was the PI for STARS, which was suggested to ESA at the same time. But thanks for this talk.
The paper booklet that I have from CoRoT at that time has Claude as the PI.
No, that's just sort of some kind of confusion. She was,
good, thank you.
And she was always the PI.
Clearly, it's Annie that drove the mission forward.
Well, thank you for this very, very nice overview of the history. It sort of really brings back memories. Just one, I would say, correction, if I may. I think in 1995, you might have included Exoplanet as positive detection of solar-like oscillations in the subgiants with identified frequencies, even though some people didn't believe it. And that won me 6 elephant beers from Steve Kowalla, because we had a bet in 1995 whether the frequencies were real. And he conceded about 8 years later, after further observations had been made of that star. So I think that was, in that sense, the start of the detection of frequencies that could be interpreted in a scientifically meaningful way for solar-like oscillations in other stars.
Yes, thanks, Ron. That was really wonderful. I wanted to add one thing that Kepler did, which some of us at least were worried about, and that was the very bright end stars, the saturated stars. And I can remember being at conferences where you assured us that it would be okay and that Kepler would be able to do photometry on the very brightest stars, because of course they were always the ones with the parallaxes and the interferometry. And it worked, you were right, and so well done.
Thank you.
Next question.
Thank you. Thank you for this very difficult talk, and personally I agree with the view you gave of these historical events in general, so I will not discuss specific dates, but I would add to what you showed, because you stressed the way this revolution occurred in terms of numbers. But I think there is something more than numbers.
Oh,
for instance,
absolutely.
for planets, it's not the same to have planets, to know that they are planets, and to have planets characterized with very precise mass, radius, and so on. And this is part of the revolution brought by CoRoT and Kepler.
I couldn't agree more, absolutely.
And for the seismology, the same occurred, in my opinion, because before CoRoT measurement, we had no line width measurement, no real line width measurement, or amplitude measurements. So I think there has been a great revolution in this sense also.
I completely agree. It's the qualitative advances, not the numerical ones, that are most important here.
Okay, thank you very much. We have to